Okay, so welcome back to another video. So in today's video we have the following non-trivial differential equation. Well, really we're being asked to find a function f of x such that f prime of x is equal to f of x. So really the premise here is that we want to find a function that satisfies the following conditions. And for this to work, in order to do that, we would have to make a guess of a function of our choice and verify that such that we actually can achieve the condition that we want to show. And typically, now really, before I show the work, I'm not gonna write down this part of the solution, but rather if you were to take a little inspection and say we let f of x equals 0, for example, pretty much all the conditions are met. So f prime of 0, well really f prime of x equals 0, and then if you plug f of 0, then it's still 0, then everything is met. So, but that doesn't really make things interesting. Like, what if we want to consider other solutions out there that's not simply just for f of x equals 0? So that's really what we want to find, and hence that's why we want to make a guess of a function such that it satisfies this, rather than just calling it quits and saying f of x equals 0 and then ending it there. So how about that? Let's actually just find a solution. Let's actually make a guess and see what we can come up with. So typically when we're making a guess of a typical function we want to find in order to satisfy this differential equation, generally polynomials are the way to go. So of course we can write f of x and then set that equal to beta times x to the power lowercase gamma. Now of course generally with these constants we look at the real number system, but how about we actually go a little further and think of maybe from the complex number systems. Maybe we might achieve something there and get a solution that verifies the following. We never know. That's the whole point of this whole guessing game when we're coming up with functions. So really that means beta and gamma, we want to say that they're actually part of the complex number system. So now if I were to take the derivative of f prime of x, so then we have this will be beta times lowercase gamma times x to the power gamma minus 1. Okay, now how about we do our f of x, and so that means I'll plug our, so really this will be f of, then we have beta x lowercase gamma, and so that will just be beta, then put this input back over here, and then to the power gamma. So we show the work, so we have beta to the power gamma, and then x gamma, and then multiply with the gamma for the exponent, so it's gamma square. So then we have, and then multiply with the beta over on the outside, so we have beta to the power gamma plus 1, and then multiply with lowercase gamma, or excuse me, x to the power gamma square. Okay, so now how about we actually plug the two equations together, or rather set the equations equal to each other. So f prime of x equals f of x. So what that gives us is that, let's see, f prime of x, that will be beta, then gamma x, gamma minus 1, that is equal to beta, gamma plus 1, and then x to the power gamma square. And now how about I divide gamma by both sides, so the gamma will just cancel from the left hand side, and now we divide gamma by that side, but the plus 1 will just disappear, so we're just left with beta to the power gamma, and then x to the power gamma square. So how about now let's actually compare the coefficients and the exponential terms from both equations. So what this means is that I'll set the outside constants equal to each other, the coefficients specifically. So we have that this is, so we have two equations. So we have that, we have beta gamma is equal to gamma. And then another one that we have that, now we set the coefficients, or I mean the exponents equally to each other. So we have gamma square is equal to gamma minus 1. The right equation actually seems a little bit easier to show. Now I can actually subtract, let's see, we have gamma squared minus gamma, then plus 1 equals 0. You can easily find the solutions for gamma. You can either use completing the square or use the quadratic formula. Typically, I'm actually just going to use the quadratic formula, so that's easier. So we said gamma, and so we let the coefficients with our b, a, and c, you know, the quadratic formula, everybody knows that. So we have that this is negative b, so that's 1 plus or minus the square root of, so b would be negative 1, so negative 1 squared minus 4, 1, and then 1 again, and then divide this by 2 times 1, and so we get that gamma is equal to 1 plus or minus, let's see, 1 minus 4, negative 3, so that means square root of negative 3, so that'd be I, and then times the square root of 3 divided by 2. So really we have that gamma is equal to 1 plus I square root of 3 divided by 2, and 1 minus I times square root of 3 divided by 2. And now I could just really write it as plus or minus, but we'll get to that later. So now we have that gamma is equal to 1/2 plus or minus I, and then square root of 3 divided by 2. What I can do from here is that I'll just convert this to polar form, and we get that this is actually just equal to e to the power plus or minus I times what is it, pi divided by 3. And now the last thing is we have gamma square, or beta square equals, or that's supposed to be beta gamma. Oops. We have that beta gamma is equal to gamma. What I'll do is I'll just take the I'll just take the gamma root. So we'll have beta is equal to gamma to the power 1 over gamma. Okay, so we found our beta and our gamma, so let's actually go back to our f of x. So f of x, we said that that's equal to beta and then x times gamma. So really, we just have to plug in our our evaluated, or our constants rather. So we have that this is beta 1 over, or gamma to the power 1 over gamma, and then x to the power gamma. Now the last thing is just plug in our gamma. For this one, gamma for this term in particular, I'm going to keep it in the polar form, and then gamma over here, I'll with x to the power gamma, I'll write it out as its evaluated polar form. So then we have that this is, let's see, this is e to the power, so plus or minus I, and then pi over 3, and then we multiply this by, well, how about this? What do I write? Well, how about I write it like this way? Since we have a plus or minus, I'll write, that generally means that we're almost done, so it means we actually have 2 solutions for our f of x. So we have that f of x, and then another f of x, just write it like that. So we have that this is e to the, and then the top f of x is going to be with the positive I. So we have, let's see, so this is I to the power pi over 3, and then 1 over positive pi, so that means I'll just change that to a negative I pi over 3, right? Yes, and then multiply with x to the power 1/2 plus I times the square root of 3 divided by 2. Okay, and then now the last one is just focusing on the negatives. So this will be e to the power negative I pi over 3. Then we multiply this by e to the, so it's 1 over that negative, so that means just change that to the negative fraction, so that'll negate the negative, so that means we have, it's a positive I times pi over 3, and then multiply with x to the power 1/2, subtract with I to the square root of 3 divided by 2. And there we have it, like so. We have our 2 solutions. we have, and basically they're just dealing with the complex numbers. So we have that, we can have that f of x is equal to e to the power I pi over 3, then times e to the negative I pi over 3 times x 1/2 plus I square root of 3, and then the second solution for the f of x is e to the negative I pi over 3 times e to the I pi over 3 multiplied with x to the power 1/2 minus I to the square I times square root of 3 divided by 2, like so. Okay, that's pretty cool if you ask me.